Hello everyone, I am Ch.Nagendra Mahesh. In this video, we will discuss about brain tumor classification using a pre-trained VIT model. Yeah. What's a brain tumor? Brain tumor is an abnormal growth of cells inside the brain. It can be benign or malignant. Benign is non-cancerous, but malignant or cancerous. Depending upon the size and location, it can seriously affect the brain function. So early need for brain detection early need for brain tumor detection is very important, as over time tumor can grow and damage your healthy brain tissues. If identified early, the chances are very high for survival. So how MRI helps in brain tumor diagnosis? MRI is the most common tool used to detect brain tumors. It gives a high resolution images of the brain without using radiation, making it safe and reliable for diagnosis. So coming to types of brain tumors, there are actually three types: glioma, meningioma, and pituitary tumor. These three will occur at different parts of the brain. So glioma occurs in glial cells, which are near the brain and our spinal cord. Meningioma develops around the membrane surrounding the brain. These are usually benign, but glioma brain tumor can be a malignant. These are cancerous. And pituitary tumor forms in the pituitary gland. They affect the hormonal balance, but they are uh, usually benign. So, what's the importance of automated classification? Manual. Uh, Traditionally, diagnosis depends upon the manual examination by the doctors, and sometimes it is subjective. Automated classification using AI like vision transformers and other CNN networks are more consistent and are much more reliable because diagnosis this supports the doctors and improves the patient care and gives us much more reliable results in a much more faster time. So what's the use of a retrained model? Like medical data sets for a particular case, they are very small and limited. Training using that much very small data sets will be leading to overfitting and poor generalization. If we use a pre-trained model like VIT or other things, like they have already been trained to learn visual features from a large data sets. So using pre-trained models is much more better because if we take any trained model, it consists of a neural network, right? To train every neural network, we need a very vast amount of data. So since we have very small data, we are going to use a pre-trained model. uh, how it helps us, like after taking a pre-trained model, we have to fine tune it, because after fine tuning it, it will be adapting to our certain case. Like in our case, we are using it for MRI scans, right? So fine tuning it will help us to adapt it to it. It also gives us faster convergence and better accuracy. So what is the advantage of a vision transformer? Vision transformer uses self-attention networks to learn the global relations between the image and its regions. Unlike CNN, like we compare it to CNN. So VIT has a long-range dependencies effectively because uh, let's say in medical field, it is very important to have a more global relationships. Like for a compared to CNN, Vision Transformer can easily adapt to new domains like MR or any other network, any other use we can think of. As in real world, CNNs are actually outperformed by Transformer networks. So let me show you how a transformer works. Consider this image. Like we will split the image uh, and feed it to the transformer. In this transformer, since it's a self-attention network, it will calculate the query key and its value. Based on these, it will calculate the attention score and attention matrix. uh, so these matrices are embedded here. So when a new image comes, it will also calculate its query key and value. So based on these things, it will assign the image positions that are already trained, and it will give us the classified image, like this is the uh, benign and other things. So let me show you our training phase. Like it's a two-phase training strategy. In one phase, like we will only go for a transformer. It's a for a dense neural network. We will only be training the head face. Like we will froze the entire region, but we will be only having the head face free so that we can train it. This leads, since we have a very small amount of data, this causes us to prevent the overfitting. If we are going to have the entire neural network and we are going to train it using this small data set, it will lead to overfitting and poor generalization. So we are planning to freeze the entire network and have only the heads to be trained. But later in the uh, lightweight tuning phase, we will be unfreezing some of the last transformer layers so that it will be trained much more better, and it will adapts the MRI features more effectively. So the optimizations that were done in this project are Adam W optimizer is used by the transformer. So Adam W optimizer is a widely used optimization algorithm in deep learning. It it adapts the learning rate for each parameter, making it training faster and more stable. So another thing is label smoothing. Instead of giving labels like 1 or 0, label smoothing slightly softens them. This actually improves the generalization much more better. Another thing is gradient clipping. Sometimes gradients can be very large and they can tend to move along the graph. So to prevent it, we use gradient clipping. This limits the maximum gradient value and ensures a smooth learning curve. And another thing is warm up and cosine decay. Uh, Initially, when we start to train a model, it gradually increases its learning rate. But after a certain point, it drops drops at a higher pace. So to prevent it, if we use cosine decay method, it will prevent these sudden jumps, and it will reduce the decay process also, which will give us a smooth curve. And this also gives us a good convergence also. So let's get to the project code, like how it's done. These are the let's get into the coding part. So this is the code we have written. This is the dataset we have imported from the Kaggle. So number of images per class. Like this is the glioma brain tumor. It has 2004 images. And this is menin brain tumor. It has 2004. And pituitary gland tumor. It has 2000. All are equal datasets. So this is how each tumor will be represented in an MRI scan. This is glioma. This is menin, and this is pituitary gland. So this is we are pre-processing the data sets. Like we are splitting the data sets into 70% for training, 15% for validation, and 15 for testing. After splitting the data sets, for training we have 4,000 images. For validation we have 900 and testing around 900. After splitting the data sets, we are resizing the images and normalizing the data. We are also augmenting the data, like since we have a very less data set, we are giving the same image in different ways. Like you see here, uh, this is how the many MRI scan is, like we are giving it in a different way. This is one of the example for augmentation. And now here we are importing the transformer model. These are the inner layers of of the transformer we have imported. This is the input layer. This is the pre-processing layer and HV80 layer. And these are the dropout and dense layers. Dropout is actually a very good generalization method. In a neural networks, drop. We are going to drop the neurons randomly using the in the dropout. Like in a dense neural network, for we will drop out the neurons randomly such that each neuron will be trained accordingly i- with irrespective of the weights that are already predefined. So in the learning rate, we are using our warm-up plus cosine as we discussed earlier. And now let's get into the training part. Uh, for the predefined transformer, we are actually training only heads. This is how we are going to do it. Uh, this code works like uh, for the given data, if the since transformer is a feedback model, so as long as the accuracy keeps on increasing, the transformer works. Uh, so you see like here that the transformer is working as long as the accuracy keeps on increasing. From after 88.49, when the accuracy is going to drop, the transformer stops working. So the initial pre-training is completed here with an accuracy of 88.49%. After that, we are going to fine tune the model, like unfreezing the previous networks, and then we are going to run the model again with the data such that it will be familiarized with the MRI scans. So after that, the accuracy is improved to 90%. This is because like since we have a very small data set for MRI scans, the data is insufficient, causing the accuracy to be around 90%. These are the loss and fine loss curves during the head training and after fine tuning. These are the accuracy curves. Like this is the when we are training the loss function curve. After validating, this is for the validation set. This is the loss function curve. These are the accuracy curves. This is the training accuracy curve after fine tuning. For validation, we got around 87 percentage. For the final testing, we have imported a data set and we have used it. These is the accuracy. We got 91.64% with a loss of 0.3. This is the confusion matrix, glioma, menin, and tumor. After this is the classification report with a precision of 92.52% for the glioma and 95% for menin and 87% is tumor. From this data, we can say that the images that we have taken is much more suitable for menin. But if we have a good data set and we have more number of images, we can improve the accuracies for each of the tumor. This is how the model recognizes the tumor for each classification. Here we can see if the image consists of this type of part, it will be classified as menin. Uh, and if the image consists of the tumor image like this, then it will be considered to be a glioma. If the tumor consists of like this at the edges of the scan, then it will be like pituitary tumor. This is how the scans are. This is how the model recognizes the tumor and classifies it into it. So that's it. Right.